The nearest galaxy to ours is so far away that even light, the fastest thing in the universe, takes 2.5 million years to cross the gap. 2.5 million years. Before humans existed. Tonight we cross that void. We meet a galaxy being eaten alive by our own. We find half the universe is missing matter, hiding in empty space. And we watch two galaxies fall toward each other in a slow-motion crash that will reshape everything. If you enjoy this journey, like and subscribe. It keeps us going. Let's begin. Picture the edge of our galaxy, a swirling outer rim of old stars, dust clouds, and sparse light. Scientists spent decades mapping that region, convinced they understood what lived there. They were wrong. In 2003, a team of astronomers was doing a routine sky survey. They were looking for patterns in star density, mapping the outer Milky Way the same way you might trace the edge of a city on a map. Then something strange showed up. A cluster of stars that was too organized, too concentrated, too consistent to be random. Stars grouped like that do not just happen, they belonged somewhere. The team cross-checked the data. They measured distances. They confirmed, rewrote the record books. Hidden right at the edge of our galaxy, buried inside the outer disk like a secret tucked under a rug, was an entirely separate galaxy. Scientists named it the Canis Major Dwarf Galaxy, after the constellation it sits behind, from our view. Here is the part that hits hardest. It was not sitting out in open space waiting to be spotted. It was so close and so tangled up with our own galaxy's outer structure that we looked right past it for generations. Every telescope pointed outward, scanning millions of light years into deep space, completely missing a galaxy practically touching our own. The Canis Major Dwarf Galaxy sits about 25,000 light-years from our position in the Milky Way. To picture that distance, consider this. The center of our own galaxy is about 26,000 light-years away from us. That means this separate galaxy, this entirely different cosmic structure made of its own ancient stars, is actually closer to us than our own galaxy's core. Let that geography sink in. A foreign galaxy sits nearer to you than the heart of the galaxy you live in. A spacecraft moving at the speed of our fastest probe Voyager would take 749 million years to reach it. 749 million years just to reach the closest one. And even that number will change in a dramatic way, because the Canis Major Dwarf Galaxy is not just sitting there quietly. Scientists confirmed it is being pulled apart. Our galaxy's gravity is stretching it, stealing its stars, absorbing its outer edges like a slow-moving tide pulling sand off a beach. Some of its stars have already crossed into our galaxy's outer arms. Right now, stars born in a completely different galaxy are drifting through the same cosmic neighborhood as our own stellar family. This discovery forced astronomers to reconsider something basic. If a whole galaxy could hide inside the edge of our own for this long, what else are we missing? What other structures exist so close, so embedded in familiar scenery, that our instruments simply look through them? The answer turned out to be stranger than anyone expected, because even after finding Canis Major, scientists kept digging. They found another galaxy, one that sits even deeper inside our own borders. A galaxy being actively devoured, its stars stretched into long streams that wrap around the Milky Way like a ribbon around a gift. And that one had been hiding even longer. For most of modern astronomy, the answer to which galaxy is nearest to us seemed settled. Scientists pointed to the Magellanic Clouds, two bright smudges visible in the southern night sky, and called it done. The Large Magellanic Cloud sat about 179,000 light-years away, close enough, they figured, to be our nearest galactic neighbors. Case closed. Except it was not. The problem was not that scientists were careless. The problem was that finding a nearby galaxy is surprisingly hard. You might think closer means easier to spot, the same way a streetlight nearby looks brighter than a distant city skyline. But galaxies are spread across enormous patches of sky. When a galaxy is small, old, and dim, Its stars blend into the background, like a crowd of people all wearing the same grey coat. Your eye slides right past them. In 1994, a research team was studying a dense region of sky in the direction of the Sagittarius constellation. They were mapping star motions, tracking how individual stars moved over time to understand the galaxy's structure. One group of stars behaved oddly. Their velocities matched each other too well. Their ages were too similar. They moved as a unit rather than as random members of the Milky Way's halo. They found they were looking at a galaxy, the Sagittarius Dwarf Elliptical Galaxy, sitting about 70,000 light-years away. Suddenly, the Large Magellanic Cloud lost its title. A new record holder took over, one that had been hiding in plain sight for the entire history of modern astronomy. Then 2003 arrived, a different team, using infrared light that pierces through dust clouds better than visible light, caught something even closer. The Canis Major Dwarf Galaxy, at 25,000 light-years, beat every previous record. 3 different record holders in under a decade. Each discovery shared the same pattern. Scientists looked in a familiar direction and found something invisible to earlier tools. The Sagittarius Dwarf Galaxy was invisible not because it was far, but because older telescopes could not pick out its old, dim stars from the Milky Way's own outer halo. Infrared technology changed everything. Suddenly, the universe's backyard looked very different. This back and forth matters beyond the record books. Every time the closest galaxy changed, scientists had to revise their models of the Milky Way's structure and mass. A galaxy sitting 70,000 light-years away pulls on us differently than one at 179,000. Each discovery refined the map of gravitational forces shaping our home galaxy, and the debate is not fully settled. Astronomers still disagree about whether a few other dwarf structures qualify as galaxies, or are simply large clusters of stars. The line between a galaxy and a very big star cluster gets blurry at the small end of the scale. Several candidate objects in our galaxy's halo remain uncategorized. Each one could be a new record breaker hiding in data we already have. The tools keep improving, the maps keep changing, and beneath all of this sits a strange reality. We still have not finished cataloging our own cosmic neighborhood. There are likely dwarf galaxies nearby that we have not found yet, buried inside the Milky Way's outer disk, the same way Canis Major was for so long. But the galaxy we have found closest to us is already falling apart. And what is pulling it apart says a great deal about the enormous, invisible force running through our galaxy. That story gets even more dramatic when you realize what it means for another neighbor, one that is not a dwarf, one that is a giant, and it is heading straight for us. Stop for a second. Every number in this story involves light years, and if that term sits in your brain as just a vague, really far, everything that comes next will feel hollow. So let's fix that right now. A light year is a unit of distance. People sometimes think it measures time because the word year is in it. It does not. It measures how far light travels in one full year. 1 year of constant motion at the fastest speed the universe allows. Light moves at 186,000 miles per second, not per hour, per second. In a single second, a beam of light travels far enough to circle the entire Earth 7.5 times, 7.5 laps around the planet, in 1 second. Now run that for a full year, 365 days. Every second, 7.5 laps around Earth. Let it run for an entire year, without stopping. The distance you get at the end of that year is 1 light year. Scientists have calculated it precisely. 1 light year equals about 5,880,000,000,000 miles. That number is too large to hold in your head. So try this. Imagine driving a car at 60 miles per hour, no stops, no sleep, forever. To cross 1 single light year, that drive would take about 11 million years. 11 million years of highway at 60 miles per hour for 1 light year. The nearest major galaxy sits 2.5 million light-years away. Multiply that 11 million year drive by 2.5 million. There is no number large enough to write that down in a way the human brain respects. The mind simply deflects it, the same way you stop feeling cold after being outside long enough. The scale stops registering. This is why astronomers use light years instead of miles. Miles break down completely at galactic distances. Even light years feel almost too small once you start talking about the space between galaxy clusters. Here is another way to feel the distance. The light entering your eye right now left the Andromeda Galaxy 2.5 million years ago, before the first humans walked upright on this planet, before stone tools, before language. That light started its journey when our ancestors were still figuring out how to use a sharp rock, and it just arrived tonight. You are looking at the past every time you look at the night sky. Every star you see is a time capsule. The farther the object, the older the light. Some stars you see tonight burned out thousands of years ago. You are watching a ghost, 1 light year, 5,880 billion miles, and the nearest major galaxy is 2.5 million of those, stacked end to end. And yet somehow, for most of human history, nobody knew Andromeda was even a separate galaxy. To the naked eye, it looks like a faint smudge, smaller than your thumbnail held at arm's length. Something that small and soft-looking contains 1 trillion stars, and it is falling toward us. But before we get to the collision, it helps to understand just how impossibly slow any attempt to travel that distance would actually be, because the numbers about spacecraft travel times are the most humbling ones in this entire story. They make the universe feel like a locked room with no door. 186,000 miles per second. Say that number out loud and it sounds fast. It sounds like the answer to every problem. Build a ship that fast, point it at Andromeda, and go. Here is why that logic collapses the moment you apply it to real distances. At the speed of light, crossing our own Milky Way from one edge to the other takes 100,000 years. 100,000 years at the fastest speed physics allows, just to cross our home galaxy. No stops, no delays. Perfect, uninterrupted light speed travel for 100,000 years. Now look outward. Andromeda sits 2.5 million light years away. At light speed, that journey takes 2.5 million years. A ship built today, traveling at the absolute universal speed limit, would arrive at Andromeda long after every human institution, every language, every civilization that exists right now has vanished completely from memory. Light speed is so fast, it laps Earth 7 times per second, and even that speed makes Andromeda unreachable within any timescale a human civilization could plan for. This is one of the most disorienting facts in all of science. Speed feels like a solution. Go faster, get there faster. But the universe's distances are so enormous that they swallow speed entirely. They do not care how fast you go. The gap wins. There is a physics reason for this too. According to Einstein's work on relativity, which has been confirmed in countless experiments, nothing with mass can actually reach the speed of light. Light itself can travel at light speed because it has no mass. Any physical object, any ship, any particle with mass would require infinite energy to reach that speed. So a real spacecraft, made of real material, with real people inside, could never hit light speed. The best theoretical designs that physicists take seriously might someday reach a small fraction of light speed. Some proposals suggest 10%. A few ambitious ideas push toward 20 or 30%. Even at 30% of light speed, the trip to Andromeda takes over 8 million years. The closest confirmed galaxy, Canis Major, at 25,000 light-years, would still take 80,000 years at 30% light speed. A round trip would take 160,000 years. No crew survives that, no mission plans for it. No civilization maintains contact across that time frame. Scientists know all of this. They have run the numbers in every direction. The conclusion lands the same way every time. The distances between galaxies are so large that they function as a permanent wall, at least with the technology and physics we currently understand. Some researchers study theoretical shortcuts, concepts like bending space-time or finding passages through it. Those remain in the realm of math, with no known path to building anything real. Most physicists consider them extremely unlikely to ever be practical. So we sit here, one species, one planet, one solar system inside one galaxy, aware of 2.5 million light-years of open void between us and the nearest major neighbor, aware that we cannot cross it, aware that our fastest machine, already launched and still traveling, makes the situation look even more staggering. That machine is already out there, already moving, already old. And the distance it would need to cover to reach even the nearest dwarf galaxy is a number that will make light speed feel almost slow. Almost. In 1977, humanity launched 2 spacecraft into the dark, Voyager 1 and Voyager 2. They were built to tour the outer planets, swing past Jupiter and Saturn, collect data, and eventually drift into interstellar space. Nobody expected them to still be transmitting almost 50 years later. They are. Right now, Voyager 1 sits over 14 billion miles from Earth. 14 billion miles. That sounds enormous. Against the distances in this story, it is a single step out the front door. Voyager moves at about 38,000 miles per hour. That speed took decades to build up using a technique called gravitational assist, where a spacecraft slingshots around a planet's gravity to gain speed without using fuel. Voyager squeezed every advantage from the physics available to it in 1977. 38,000 miles per hour is the result. At that speed, crossing 1 light-year takes about 18,000 years. The Canis Major dwarf galaxy, our closest galactic neighbor at 25,000 light-years, would take Voyager approximately 749 million years to reach. 749 million years. To give that number texture, 749 million years ago, the most complex life on Earth was single-celled organisms drifting in shallow seas. Humans, mammals, dinosaurs, fish, and even most plants had not yet existed. Voyager would arrive at Canis Major when whatever comes after humans, after every species alive today, has long since risen and fallen and been replaced by something unrecognizable. And Voyager is our fastest spacecraft, the fastest machine humanity has ever sent into space, the best we have done so far. There is a concept physicists use called the Tsiolkovsky rocket equation. It describes how much fuel a rocket needs to accelerate. The brutal result: the faster you want to go, the more fuel you need, and the more fuel you carry, the heavier your ship becomes, which means you need even more fuel to move that weight. The math spirals against you fast. Building a conventional rocket to cross galactic distances is not just hard. The numbers become physically impossible long before you approach light speed. Some researchers have proposed a different approach called a solar sail, a massive, thin reflective sheet pushed by the pressure of light from a powerful laser. The breakthrough Starshot project floated the idea of sending small probes toward the nearest star system at 20% of light speed this way. Even at 20% light speed, Canis Major would take 125,000 years to reach. Every proposal leads to the same answer. The nearest dwarf galaxy is permanently out of reach for any physical object we could realistically build. The distances are so large that they stop being a travel problem and start being a philosophical one. Humanity stands at the edge of a void and can see across it, measure it, map it, understand its structure, and predict its future. What we cannot do is cross it. And yet something crossed it. Something already lives on the other side and has been falling toward us for billions of years. The collision it will cause will be the largest single event in the future history of the solar system. But first, there is a galaxy currently being torn apart and consumed right now, in near silence. And it has been happening so slowly that nobody noticed until we had the tools to see the evidence written in streams of stolen stars. That galaxy is closer than the center of our own, and it is already half-eaten. Somewhere behind the dense dust and stars of the Milky Way's core region, a galaxy is being destroyed. Slowly, silently, completely. The Sagittarius Dwarf Elliptical Galaxy sits about 70,000 light-years from us. It held the record as our closest galactic neighbor for nearly a decade before Canis Major took that title. But its proximity was never its most dramatic feature. The dramatic feature is what our galaxy is doing to it. The Milky Way is enormous. Its gravity reaches far beyond its visible edges, pulling at everything in the surrounding region like an invisible hand dragging objects across a table. The Sagittarius Dwarf has been orbiting inside that gravitational grip for billions of years. Each orbit pulls it closer. Each pass near our galaxy's disk strips away more of its stars. Think of it like a sandcastle at the edge of the tide. Every wave that rolls in pulls a little more sand away. The castle keeps its shape for a while, but the erosion is relentless. The Sagittarius Dwarf Galaxy is that sandcastle. Our galaxy is the ocean. Scientists who study its structure have confirmed that the galaxy has already completed multiple orbits around the Milky Way. During each orbit, tidal forces rip stars from its outer layers and stretch them into long, curving streams. Those streams now wrap around the entire Milky Way in ribbons of displaced stars, stars that were born in a different galaxy, drifting now through our own galaxy's halo. In 1994, the team that discovered this galaxy mapped one of those streams across a significant portion of the sky. The stream is called the Sagittarius Stream, and it is one of the longest known stellar structures associated with our galaxy. It stretches hundreds of thousands of light-years, a scar left by repeated gravitational violence. What remains of the Sagittarius Dwarf Galaxy is a dense core, an older population of stars clinging to each other, while everything around them gets pulled away. Scientists estimate the galaxy has lost the majority of its original mass to the Milky Way over billions of years. And the orbit is not done. The Sagittarius Dwarf will swing around again. Each pass strips more away. Eventually, over many more billions of years, the core itself will dissolve into the Milky Way's halo. A galaxy that once existed as its own structure will become part of ours, its identity erased, its stars absorbed. Right now, as you listen to this, that process is underway. Stars from Sagittarius are inside our galaxy's halo. Some may be close enough to see from Earth with the right equipment, an entire galaxy being consumed over billions of years, and we caught it mid-meal. This is not unique to the Sagittarius Dwarf. Our galaxy has consumed others before. Scientists find the evidence in the Milky Way's halo, where streams and shells of stars with unusual properties hint at past mergers. The Milky Way grew partly by absorbing smaller neighbors over its long history, which raises an uncomfortable thought. If our galaxy has been eating its neighbors for billions of years, what does that say about the future? One neighbor is not small at all. It contains 1 trillion stars, and it is falling toward us right now. But to understand the scale of that approaching collision, you first need to understand just how impossibly vast the space between us actually is. And one specific number will do most of that work. That number belongs to an object so familiar it has a name everyone knows. But almost nobody knows its real size. Here is a fact that breaks the brain a little. The center of the Milky Way is about 26,000 light-years from our position in the galaxy. The Canis Major Dwarf Galaxy sits about 25,000 light-years away. A foreign galaxy is physically closer to us than the core of the galaxy we live inside. That should feel wrong. It does to most people when they first hear it. You are inside the Milky Way, so its center should be the nearest significant point, right? But the Milky Way is enormous. Our solar system sits in one of its outer spiral arms, roughly 2/3 of the way out from the center. That puts us far from our own galaxy's core and close to the galaxy's edge, where a small neighbor can tuck in surprisingly near. Canis Major sits just below the plane of the Milky Way in the outer disk region, the same region our solar system occupies, which is exactly why it stayed hidden so long. Canis Major's stars sit scattered across a wide patch of sky that overlaps heavily with our own galaxy's outer disk. When you look in that direction, you see Milky Way stars in front and behind, with Canis Major stars mixed in between. Separating them required infrared observations and careful velocity measurements that older telescopes could not perform. The astronomers who found it in 2003 were not even looking for a galaxy. They were studying an unusual overdensity of stars in that region, an area where the star count was slightly higher than expected. When they measured the distances and velocities of those stars, the pattern became clear. These stars moved together. They formed a coherent structure. One of the ways scientists confirm that a group of stars belongs to a separate galaxy is by studying their chemical makeup. Stars born in different galaxies carry slightly different ratios of elements, reflecting the unique history of star formation in that environment. The Canis Major stars showed chemical signatures distinct from typical Milky Way halo stars. That was one of the key pieces of evidence. Canis Major is classified as a dwarf irregular galaxy, meaning its shape has been heavily distorted, likely by exactly the same gravitational tidal forces pulling apart the Sagittarius dwarf. Streams of stars from Canis Major have also been identified curving through our galaxy's outer disk, evidence that our galaxy is in the process of consuming this one too. So right now, our galaxy is simultaneously eating two of its closest neighbors, Sagittarius from one side, Canis Major tucked into the outer disk below. Both are dissolving into the Milky Way over billions of years, their stars becoming part of our galaxy's outer structure. This process has happened before. It will happen again. The Milky Way is a galaxy built in part from the ruins of smaller galaxies it absorbed over its 13 billion year life. And while all of this quiet consumption happens in our outer disk, something entirely different lives in the opposite direction. Two small galaxies hanging in the southern sky, visible to the naked eye from the right locations on Earth, have been our most well-known neighbors for all of human recorded history. Most people have heard of them. Few people know the strange reality of what they actually are and where they are going. What comes next in their story is a slow-motion catastrophe that has already begun. For centuries, sailors navigating the southern seas used two blurry patches of light in the night sky as reference points. They did not know what those patches were. They looked like detached pieces of the Milky Way, faint glowing clouds hanging in the dark. Portuguese and Spanish sailors in the 15th and 16th centuries noted them carefully. The European explorer Ferdinand Magellan's crew documented them during their circumnavigation of the globe, and they eventually became known as the Magellanic Clouds. The larger of the two, now called the Large Magellanic Cloud, sits about 179,000 light-years away from us. For most of modern astronomy, that was close enough to claim the title of nearest galaxy. The Large Magellanic Cloud held that record for decades, right up until 1994, when the Sagittarius dwarf galaxy was discovered. Even after losing the title, the Large Magellanic Cloud remains one of the most studied galaxies in the universe precisely because of its proximity. At 179,000 light-years, astronomers can see individual stars inside it, study their life cycles, and watch phenomena that would be invisible in more distant galaxies. The Large Magellanic Cloud is classified as an irregular dwarf galaxy. Its shape is ragged and asymmetric, pulled out of any orderly form by gravitational interactions with the Milky Way and with its companion, the Small Magellanic Cloud. It spans roughly 14,000 light-years across. By galactic standards, it is small, but relative to the Milky Way, it is substantial enough to create real gravitational effects. Scientists have confirmed that the Large Magellanic Cloud is massive enough to warp the disk of the Milky Way itself. Our galaxy's outer disk is not flat, it bends, and a significant portion of that bending was caused by the gravitational pull of the Large Magellanic Cloud over billions of years. Inside the Large Magellanic Cloud lives one of the most famous nebulae in the night sky, the Tarantula Nebula. It is a region of active star formation so intense that if it sat at the same distance as the Orion Nebula in our galaxy, it would cast visible shadows on Earth at night. The Tarantula Nebula is about 1,000 light-years across, containing millions of young stars, including some of the most massive stars ever confirmed. In 1987, a star inside the Large Magellanic Cloud exploded in a supernova. Astronomers were able to study the explosion in extraordinary detail because of how close the Large Magellanic Cloud sits relative to other galaxies where supernovas occur. That event, called Supernova 1987A, remains one of the most studied stellar explosions in history. The light from it took 179,000 years to reach Earth, carrying information about the physics of a dying star that no instrument on Earth could replicate. The Large Magellanic Cloud is heading toward us, slowly by human standards, fast by galactic ones. Some models suggest it will eventually merge with the Milky Way, though the timing and path depend on variables scientists are still measuring. But compared to what awaits us from another direction entirely, the Magellanic Cloud's approach is almost gentle. 2.5 million light-years away, something far larger is falling toward us, with the momentum of 1 trillion stars behind it. And that galaxy has been heading our way since long before Earth formed. What happens when you finally look at it in the night sky? You will see something far bigger than most people ever realize. The small Magellanic Cloud sits about 210,000 light-years away. It is slightly farther than its companion, the Large Magellanic Cloud, but the two move through space together, bound by their shared gravity, traveling as a pair through the Milky Way's outer neighborhood. Think of them like two rocks tied with an invisible string, orbiting each other, while both are pulled towards something much heavier. The Milky Way is the heavier thing. The small Magellanic Cloud is smaller and more irregular than its companion. It spans roughly 7,000 light-years across, roughly half the width of the Large Magellanic Cloud. Despite its size, it contains hundreds of millions of stars, many of them young and actively forming. Its irregular, patchy shape is the result of tidal forces from both its companion and from the Milky Way, stretching its structure over billions of years. One of the most striking features connecting both Magellanic Clouds is a bridge of gas and stars called the Magellanic Bridge. This structure stretches between the two galaxies, a stream of material pulled out from both of them by their gravitational interaction. Scientists have confirmed that stars are actively forming inside this bridge right now, stars being born in the space between two galaxies, in a region that was once just drifting gas. There is also a structure called the Magellanic Stream, a ribbon of hydrogen gas stretching from the Magellanic Clouds across a massive arc of the sky, trailing behind them as they orbit the Milky Way. This stream extends for more than 100 degrees across the sky from our perspective, an enormous feature created by the Milky Way's gravitational drag on the gas in both galaxies. The fate of both Magellanic Clouds is uncertain. Some models suggest they are on their first pass near the Milky Way, moving fast enough that they might eventually escape our galaxy's gravity and continue into deeper space. Other models suggest they are already on a trajectory that leads to eventual merger with the Milky Way billions of years from now. Scientists are still working to constrain the exact velocities and trajectories needed to settle the question. What is confirmed is that both clouds are close enough to interact with us physically. The Milky Way is pulling on them, they are pulling on the Milky Way, and the bridge of stars and gas between them shows that they are pulling on each other. This three-way gravitational relationship is actively shaping all of them. The small Magellanic Cloud also holds one practical record of importance to astronomy, because it sits at a known distance and contains many stars of a particular type called Cepheid variables. stars that pulse in brightness at a predictable rate related to their actual luminosity. It helped early 20th century astronomers build the first reliable cosmic distance ladder. The work done using stars in the Magellanic Clouds helped prove that Andromeda was millions of light-years away, changing our entire picture of the universe. That discovery, made in the early 1900s, transformed everything astronomers thought they knew. One measurement, one type of pulsing star, and it flipped the entire human understanding of how large the universe actually is. The person who made that measurement almost did not get credit for it, and the story of how that happened is one of the strangest injustices in the history of science. Right now, mixed into the outer edges of our galaxy, there are stars that were born somewhere else. They formed in the Sagittarius Dwarf Galaxy, or the Canis Major Dwarf Galaxy, billions of years ago, in a different gravitational environment, with a different mix of surrounding stars, part of a completely separate galactic structure. And now they drift through our galaxy's outer halo, permanently absorbed, their home galaxy gone or nearly gone. Scientists can identify these stars. They do it through two methods. The first is orbital behavior. Stars native to the Milky Way tend to follow orbits consistent with the galaxy's overall rotation. Stars captured from other galaxies often follow unusual orbits, sometimes tilted at odd angles to the main disk, sometimes moving in the opposite direction entirely. These misfit orbits stand out to astronomers who track stellar motion carefully. The second method is chemistry. Every star carries a chemical fingerprint in its light, a spectrum of elements baked in from the cloud of gas it formed from. Stars that formed in different galaxies carry different ratios of certain elements, reflecting the unique star formation history of that environment. Scientists can compare a star's spectrum to models of what Milky Way stars should look like and identify outliers with a high degree of confidence. Using both methods, researchers have identified stellar streams crossing through our galaxy's halo that trace back to ancient merger events. The most prominent is the Sagittarius stream, a ribbon of stars confirmed to have originated from the Sagittarius Dwarf Galaxy. This stream wraps around the Milky Way in multiple loops, covering a huge arc of the sky. It is one of the longest known structures associated with our galaxy. There is evidence of older mergers too, a structure called the Gaia Sausage, or Gaia Enceladus, named after the European Space Agency's Gaia telescope that helped discover it, represents the debris of a collision between the early Milky Way and a dwarf galaxy roughly 8 to 11 billion years ago. That ancient collision sent stars into highly elliptical orbits in the inner halo that we can still detect today. This means the Milky Way's history is written in its stars. Every unusual orbit, every chemically odd star, every unexplained stream of stars across the halo is evidence of a galaxy the Milky Way once absorbed. Our galaxy is partly built from the wreckage of others. Some of those absorbed stars are old, very old. Stars that formed in the early universe billions of years before our solar system existed, now sharing the galaxy with stars that formed much more recently. The halo of the Milky Way is essentially a museum of past collisions if you know how to read it, and this history has a practical impact right now. When scientists study the outer halo looking for these ancient streams, they sometimes find unexpected concentrations of stars. Each unexpected concentration raises the possibility of a dwarf galaxy, not yet catalogued, hiding in the halo the same way Canis Major hid in the outer disk. Astronomers believe additional dwarf galaxies around the Milky Way remain undiscovered. The current count of confirmed Milky Way satellite galaxies sits around 60, but models predict there should be more. Maybe many more. Somewhere in the sky above you right now, there may be a galaxy we have not yet spotted, dim, scattered, blending into the halo, waiting for the right instrument to pick it out. And the instrument that changed this entire field of search more than any other was not a bigger telescope. It was a dead star with a heartbeat. A star that helped humanity realize just how enormous the universe really is. In 1888, A British astronomer named Isaac Roberts set up a camera on his telescope and aimed it at a faint smudge in the night sky that astronomers had catalogued as the Great Andromeda Nebula. He exposed a photographic plate for nearly 3 hours, letting light collect in the darkness. When he developed the image, he saw something unexpected. The smudge resolved into a disk, a spiral disk with sweeping arms and a dense, bright core. Roberts published the image, one of the first photographs ever taken of what we now call the Andromeda Galaxy. At the time, nobody knew what it was. The word galaxy in its modern sense did not yet fully apply. The dominant view among astronomers was that everything visible in the night sky existed within one large structure, the Milky Way. The Great Andromeda Nebula was assumed to be a cloud of gas somewhere inside our galaxy, perhaps a region where new stars were forming. The photograph Roberts captured showed structure too organized, too symmetric, too large for a simple gas cloud. But the tools to measure its true distance did not yet exist. So it sat in the catalogues as a mystery, beautiful and unexplained. The Andromeda Galaxy contains roughly 1 trillion stars. 1 trillion. Our Milky Way contains between 100 billion and 400 billion. Andromeda is bigger. For comparison, if the Milky Way were a city the size of Los Angeles, Andromeda would be a city roughly the size of New York City and its surrounding metro area. Andromeda sits 2.5 million light-years away. The light in Roberts' 1888 photograph had been traveling through space since before the earliest stone tools existed on Earth. It departed Andromeda while our ancestors were still figuring out fire. Even at that distance, the Andromeda Galaxy covers a patch of sky about 6 times wider than the full moon. It is enormous in angular size. The reason it looks so faint and small to the naked eye is that its light is spread over that wide area, making it dim overall. Long exposure photographs reveal its true scale, arms stretching across a huge arc of the sky. Roberts could not have known what he was looking at. He had photographed an entire galaxy, 1 trillion stars in a single long exposure image, mistaken for a local gas cloud. For 35 more years, the argument continued. Was Andromeda inside the Milky Way or outside it? The answer would determine whether the Milky Way was the entire universe or just one island of stars among billions of others. The argument ended in 1923. A single observation made by one astronomer on one clear night settled the question in a way that permanently changed humanity's understanding of its place in the cosmos. The method used was elegant, almost shockingly simple, and it depended on a type of star whose behavior acts like a precision clock, a clock so reliable that measuring it tells you exactly how far away the star sits. And what that clock revealed about Andromeda shocked the entire scientific world. In the early 1900s, the greatest debate in astronomy was called the Great Debate. 2 scientists stood before a packed audience in Washington and argued a single question. Was the Milky Way the entire universe, or was it just one galaxy among many? On one side, astronomers believed the Milky Way contained everything. The spiral nebulae, including Andromeda, were gas clouds inside our galaxy. On the other side, a smaller group argued those spirals were island universes, separate galaxies too far away to resolve into individual stars, with the tools of the time. The debate had no winner that night. The evidence was not strong enough yet for either side. Then Edwin Hubble took over the Mount Wilson Observatory's 100-inch telescope, the most powerful in the world at that time, and turned it toward Andromeda. Hubble was searching for a specific type of star called a Cepheid variable. These stars pulse. They brighten and dim in a regular cycle, like a cosmic lighthouse. The key was a discovery made years earlier by Henrietta Swan Leavitt, a woman working at Harvard Observatory, who was officially classified as a human computer, meaning her job was to measure and record data calculated by others. While doing that work, she discovered a precise relationship between how long a Cepheid's pulse takes and how bright the star actually is. Measure the pulse, get the true brightness, compare to how bright the star appears from Earth, calculate the distance, a clean chain of logic that turns pulsing starlight into a measuring tape for the universe. Hubble used this method on Andromeda. He found Cepheid variables inside it and measured their pulses carefully over weeks. When he ran the calculation, the answer came back at roughly 900,000 light-years away. His original estimate was off due to calibration issues, but the conclusion was unmistakable. Andromeda was hundreds of thousands of light-years away, far beyond any possible edge of the Milky Way. Andromeda was its own galaxy, a separate island of stars. And if Andromeda was a galaxy, then every spiral nebula in the sky was likely a galaxy too. The scale of the universe expanded overnight. One observation, one calculation, and humanity's map of reality grew by an incomprehensible factor. The Milky Way was no longer the universe. It was one galaxy, one among what we now know are roughly 2 trillion observable galaxies in the universe. Hubble published his findings in 1924. The great debate was over. Leavitt, whose discovery of the Cepheid period luminosity relationship made the entire measurement possible, never received the Nobel Prize. She died in 1921 before the full impact of her work was understood. Nobel Prizes are not awarded posthumously. The scale of the universe she helped reveal is staggering. 2.5 million light-years to the nearest major galaxy. 2 trillion galaxies visible from Earth. And yet the universe does not stop at what we can see. Even looking at Andromeda directly, you are not seeing it as it is. You are seeing a 2.5 million-year-old image of it, a snapshot from the deep past, delivered to your eye tonight in real time. What the galaxy looks like right now, in this moment, is completely unknown. The light showing you that is still on its way. Hold your hand up to the night sky and spread your fingers. The full moon fits comfortably inside your palm, held at arm's length. It spans about half a degree of sky. That is how astronomers measure angular size, how wide an object appears from Earth, regardless of how far it actually sits. The Andromeda Galaxy, if you could see all its light at once, spans about 6 times the width of the full moon, 6 palm widths of sky. That is an enormous swath for something 2.5 million light-years away. If you can find a dark sky away from city light pollution, you can spot Andromeda's core with the naked eye. It appears as a faint, elongated smudge, slightly brighter than the surrounding dark. What you are actually seeing is only the galaxy's densest central region, the part bright enough to overcome the sky's faint glow. The full extent of its disk and outer arm stretches far beyond what the naked eye catches. Long exposure photographs of Andromeda reveal the real structure: arms sweeping outward, faint star-forming regions scattered through the disk, a bright elliptical core dominated by older stars. 2 smaller satellite galaxies, named Messier 32 and Messier 110, sit visibly close to Andromeda in these images. Both are dwarf galaxies orbiting Andromeda the same way smaller galaxies orbit the Milky Way. The fact that Andromeda looks small to most people is a matter of surface brightness, meaning how concentrated its light appears, rather than actual angular size. The moon is small in the sky but extremely bright per unit of area, so it is easy to see. Andromeda is much larger in angular terms, but spread so thin across the sky that most of it blends into the background darkness. Andromeda's true diameter is about 220,000 light-years across. Our Milky Way spans roughly 100,000 light-years from edge to edge. Andromeda is more than twice as wide. Put them side by side in your imagination. One galaxy the size of a dinner plate, and next to it another galaxy nearly the size of a cutting board. If you stood on a planet near the outer edge of Andromeda and looked back toward where we sit, our Milky Way would appear as a similar faint smudge in your night sky. 2 galaxies staring at each other across 2.5 million light-years of empty space. But the space between them is not completely empty. And what fills that space, and what it tells us, has been one of the longest-running mysteries in modern science. Every measurement of the universe kept coming up short. Scientists could add up all the atoms in all the stars of all the galaxies and still only account for half the ordinary matter they expected to find. Where was the rest? The answer was in the void between galaxies, hidden in a form almost impossible to detect, and finding it took decades, a groundbreaking new tool, and 60 precise cosmic signals fired from billions of light years away. That discovery reshaped our understanding of what the universe is actually made of. But before we get there, the sheer scale of the gap between us and Andromeda deserves its own moment. 2.5 million years ago, a pulse of light left the Andromeda galaxy. It moved at 186,000 miles per second. Every second, in an unbroken line through the dark, it crossed 2.5 million light years of nearly empty space without stopping, and it ended its journey by landing on the back of your eye tonight. That is not a poetic idea. That is the confirmed physics of how light and distance work. When that light left Andromeda, Earth looked nothing like it does now. The continents held the same rough shapes, but the climate was locked in an ice age cycle. Sea levels were lower. Much of the northern hemisphere was covered in glaciers. The Mediterranean region alternated between grasslands and forests as the planet breathed through glacial and warm periods. And our ancestors. 2.5 million years ago, the species walking Earth was called Homo habilis, one of the earliest members of our genus. They were making the first known stone tools, sharp-edged rocks, chipped with deliberate strikes, simple enough that a modern person might not immediately recognize them as intentional. There was no written language, no cities, no agriculture, no civilization of any recognizable kind. The entire span of recorded human history, every empire, every invention, every war, every scientific discovery, every piece of music and literature and mathematics ever created fits inside the last tiny fraction of the time that light has been traveling. Everything you know about human history happened in the final sliver of a 2.5 million year journey. When astronomers talk about looking deep into space, they mean it literally. Every telescope is a time machine. The farther the target, the older the image. A star 1,000 light years away shows you that star as it looked 1,000 years ago, during the Middle Ages on Earth. A galaxy 200 million light years away shows you the universe as it looked before the dinosaurs existed. Andromeda shows you the universe from the dawn of human prehistory. The most powerful telescopes in existence, like the James Webb Space Telescope, can see galaxies whose light left them over 13 billion years ago. That light departed near the very beginning of the universe, when the first galaxies were just forming from clumps of hot gas. We see them as dim smudges, young and chaotic, the universe at its earliest. Every layer deeper in space is another layer further back in time. The sky is not a snapshot of the present, it is an archive of the past, lit up and visible from every point in time simultaneously. When light left Andromeda and you see it tonight, Andromeda has lived 2.5 million more years since then. Stars have formed and died inside it. Its structure has evolved. What it looks like right now, in this actual moment, is completely invisible to us. The light carrying that information is still in transit. It will arrive 2.5 million years from now. And when it arrives, our galaxy and Andromeda will be much closer together than they are today. The two are falling toward each other right now, but the approach is invisible at human speeds. To understand why they will eventually collide, and what that collision will actually look like, you first need to understand the terrifying emptiness of the space between them. 2.5 million light years. 1 light year equals about 5,880 billion miles. Multiplying that by 2.5 million gives a number with so many zeros that writing it out fills a line. Comparisons help more than math here. Imagine shrinking the Milky Way down to the size of a dinner plate, about 12 inches across. At that scale, each inch represents about 8,000 light years. The Andromeda galaxy, at 2.5 million light years away, would sit roughly 25 feet away from that dinner plate. two dinner plates 25 feet apart. That is the Milky Way and Andromeda at their current positions, 25 feet of empty space between them. Now imagine standing next to one dinner plate and trying to cross those 25 feet at a speed scaled the same way. At human walking speed, scaled to match the dinner plate model, that crossing would take longer than the current age of the universe. The ratio of the gap to the size of the galaxies themselves is what breaks human understanding. The Milky Way is enormous at 100,000 light-years across, and yet it barely fills a speck of the distance separating it from its nearest major neighbor. Think about the Pacific Ocean. It is roughly 12,000 miles wide at its broadest point, from Peru to the Philippines. A person walking at 3 miles per hour with no sleep would take about 167 days to cross it, if they could walk on water. Crossing the gap between the Milky Way and Andromeda at the same proportional scale would take a time so large it exceeds any unit humans regularly use. Light covers that gap in 2.5 million years. Walking it would take a number of years that starts with a 1 followed by more digits than fit on this page. And yet, this gap is considered close by cosmological standards. The distance between our local group of galaxies and the next major group, the Virgo cluster, is about 50 million light-years. That is 20 times farther than Andromeda. Beyond that, galaxy clusters sit at hundreds of millions and billions of light-years apart, connected by the cosmic web, the invisible skeleton of the universe's large-scale structure. 2.5 million light-years to Andromeda is our backyard, a neighborhood stroll on the scale of the observable universe. But inside that backyard, in the enormous emptiness between the Milky Way and Andromeda, something unexpected lives. Almost nothing is there. And yet almost nothing turns out to hold some of the most important matter in the universe. The question of where half the universe's matter went haunted scientists for decades. The space between galaxies looked completely empty enough to seem like a dead zone, physics-wise. But physicists working with the right tools started to suspect the void was hiding something. Something too thin to see, but massive enough to account for half of everything. To understand what they found, you first need to understand just how empty that space between galaxies really is. Because the number is more extreme than almost any comparison from daily life can capture. Galaxies do not float randomly through the universe, they cluster, they group, they form chains and sheets and knots connected by invisible threads of matter stretching across hundreds of millions of light-years. Scientists call this structure the cosmic web. The name comes from what it looks like in large-scale simulations. Galaxies clump at intersection points where multiple threads of matter cross, the same way knots form where threads cross in a spider web. Between those knots, long filaments of gas and dark matter stretch across enormous distances, linking one cluster of galaxies to another. And between the filaments are vast, nearly empty regions called voids, spaces so large and so empty that they represent the closest thing the universe has to true nothingness. Our Milky Way and Andromeda sit inside a small cluster of galaxies called the local group. The local group contains about 80 confirmed members, mostly dwarf galaxies orbiting the two large spirals. The whole local group spans roughly 10 million light-years across. The local group itself sits at the edge of a larger structure called the Virgo supercluster, a massive assemblage of galaxy groups and clusters connected by filaments of matter, spanning several 100 million light-years. The Virgo supercluster is itself part of an even larger structure called Laniakea, a supercluster of superclusters spanning roughly 500 million light-years in every direction. The cosmic web emerged from tiny variations in density in the very early universe. Just after the Big Bang, the universe was almost perfectly uniform, but almost is the key word. Tiny quantum fluctuations created regions that were slightly denser than their surroundings. Gravity amplified these variations over billions of years. Dense regions attracted more matter. Matter flowed away from emptier regions. Over time, The web grew, and the voids grew too, becoming emptier as matter drained out of them and into the surrounding filaments. The largest known voids in the observable universe span hundreds of millions of light years. Some, called supervoids, are so large and so empty that light crossing them behaves slightly differently than in normal space, affected by the accelerating expansion of the universe in a measurable way. The Milky Way and Andromeda, approaching each other at the center of the local group, are connected to this vast web by the same filaments that connect our local group to larger structures around us. We are not isolated. We sit at one node of a network that spans the observable universe. But the space between those nodes, the voids between the filaments, is almost incomprehensibly empty, and the space between galaxies, even within filaments, is emptier than anything a laboratory on Earth has ever produced. 1 atom per cubic meter. That is the average density of intergalactic space. To understand what that means and why it matters so much, you need to compare it to something familiar, something from your daily life that you would call empty. Because once you make that comparison, the gap between galaxies becomes something your brain will feel rather than just calculate. And what you feel when you truly understand that emptiness is something between awe and dread, because somehow, in that almost nothing, scientists have found half of everything that exists. You have seen pictures of space, dark, black, dotted with stars and galaxies. The blackness looks like nothing, like a place where nothing exists. The blackness between galaxies is the most extreme version of that, and it is weirder than it looks. In the intergalactic space between the Milky Way and Andromeda, there is approximately 1 atom for every cubic meter of space. 1 atom, floating alone, in a cube of space roughly the size of a standard kitchen refrigerator. Picture that refrigerator, open it, remove everything inside. Now imagine that the entire volume of the refrigerator holds exactly 1 hydrogen atom. A single hydrogen atom is so small it is invisible to any optical microscope ever built. You would have no way of knowing it was there without specialized equipment. That refrigerator of space, by any ordinary human standard, would feel completely empty. And yet by the standards of intergalactic space, that refrigerator is considered filled with matter. Here is the comparison that makes this vivid. In your lungs right now, every cubic centimeter of air contains roughly 27 quintillion molecules. That is a number 27 followed by 18 zeros. The air you breathe is packed with matter at a density that is almost incomprehensible compared to intergalactic space. Even the best vacuum scientists have created in laboratories on Earth, using powerful pumps to remove nearly all gas from a sealed chamber, still contains roughly 10 billion atoms per cubic meter. 10 billion. Intergalactic space is 10 billion times more empty than the most extreme vacuum humanity can engineer in a laboratory. This is as close to true nothingness as the physical universe appears to offer. Vast stretches of space where matter essentially disappears, where a particle might travel for millions of light years without encountering anything else, where the concept of something nearly dissolves entirely. But here is the thing that kept scientists up at night for decades. When they added up all the ordinary matter they could detect in stars, gas clouds, and galaxies, they only got about half of what the physics of the early universe predicted should exist. Half the universe's ordinary matter was unaccounted for. They called this the missing baryon problem. Baryons are the ordinary particles that make up atoms, protons. The universe should have a certain amount of them based on the conditions just after the Big Bang. But when scientists counted everything visible, half the baryons were simply gone. For years, the leading theory was that the missing baryons were hiding in intergalactic space, scattered as an incredibly thin, incredibly hot plasma, too faint to detect with conventional telescopes. The plasma was too hot to emit much visible light, too diffuse to block enough light from background sources to be easily mapped. It existed in theory. Finding proof was another matter entirely. And then, in 2025, a team found it. Using 60 precisely located signals from across the universe, they confirmed the location of the missing matter. The method they used had never been tried at that scale before, and it required waiting for a phenomenon that cannot be controlled or scheduled, only observed and catalogued. The signals that cracked the mystery had been traveling for billions of years before anyone on Earth was alive to receive them. Scientists at the world's top physics labs spend enormous effort trying to create emptiness. At facilities like CERN in Switzerland, researchers build sealed chambers and pump out nearly every molecule of gas inside them. They use multiple stages of pumping systems, cryogenic cooling, and specialized materials to get the pressure inside as low as physically possible. The goal is an environment clean enough for particle experiments, where stray air molecules would ruin precision measurements. The best ultra-high vacuum chambers achieved in modern laboratories reach pressures containing roughly 10 billion atoms per cubic meter. That number sounds tiny. In the context of everyday air, it is. But compare it to intergalactic space, and 10 billion becomes enormous. Intergalactic space holds 1 atom per cubic meter. The best laboratory vacuum holds 10 billion atoms per cubic meter. That means the emptiest space humanity has ever engineered, the most advanced vacuum technology in existence, is 10 billion times denser than the natural emptiness between galaxies. Put another way, if you took the inside of the best vacuum chamber ever built and somehow diluted it across intergalactic space, spreading every atom out evenly, each cubic meter would still contain 10 billion atoms. The universe between galaxies would have to absorb 10 billion times more matter than it actually holds just to match the density of our best artificial vacuum. There is no material on Earth that conveys this difference easily. The gap between almost nothing and intergalactic empty is so large that human engineering cannot even approach it, let alone cross it. This creates a practical problem for astronomers trying to detect anything in intergalactic space. Gas this thin does not glow the way a nebula glows. It does not block starlight the way a dust cloud does. It does not radiate in wavelengths that normal telescopes are designed to detect. At 1 atom per cubic meter, any signal produced by intergalactic matter is so faint it blends into the background noise of observations. But this matter exists. The physics of the Big Bang predicts it, and for decades it sat hidden in the gap between confirmed detection and theoretical necessity. The matter hiding in that emptiness is not cold, quiet gas. Scientists believe it exists as a plasma, a state of matter where electrons are stripped from atoms by extreme heat. This warm, hot intergalactic medium, which scientists call the WIM, exists at temperatures between 100,000 and 10 million degrees, hot enough to strip electrons from hydrogen atoms, too diffuse and too hot to glow in visible light, almost perfectly hidden from conventional observation. How do you find something that radiates almost no detectable light at a density 10 billion times emptier than our best vacuum? For decades, the answer was, you do not. You know it should be there. You build models assuming it is. But you cannot prove it. That changed when a completely different type of cosmic signal entered the picture. A signal so brief, so bright, and so precise that it acts like a bullet fired through the intergalactic medium, carrying information about everything it passed through. Scientists had to wait years to collect enough of them to do the math. But when 60 finally arrived, precisely located in the sky, the missing matter was no longer missing. In the early universe, about 3 minutes after the Big Bang, a process called Big Bang nucleosynthesis produced a specific ratio of particles, protons, neutrons, and from those, the first nuclei of hydrogen and helium. Physics locked in those ratios early, and scientists can calculate from them exactly how many baryons the universe should contain today. Baryons are the particles that make up the atoms in everything you can touch. Your body, this planet, every star, every galaxy, all ordinary matter is made of baryons. The calculation is precise, Scientists know how many baryons the universe should have. Then they went looking for them. They counted the baryons in stars, in interstellar gas clouds, in galaxy clusters. In every visible structure they could measure, they found roughly half. The other half simply was not where anyone expected to find it. Stars and galaxies account for about 10% of all baryons. Interstellar gas inside galaxies adds a bit more, but the total visible inventory stops well short of the predicted number. Half the universe's ordinary matter had no confirmed location. This became known as the missing baryon problem, and it persisted for over 20 years. Scientists had strong theoretical reasons to believe the missing baryons existed as hot plasma spread through intergalactic filaments, the warm-hot intergalactic medium. But confirming it directly was a different challenge. X-ray telescopes gave hints. Some observations caught faint signals consistent with hot gas between galaxy clusters. Ultraviolet observations found faint absorption signals in the light of distant quasars, suggesting gas along specific lines of sight. But individual detections were ambiguous. The evidence was real but scattered, and the total amount of matter they could confirm was still far short of what was missing. The problem needed a different kind of probe, something that traveled enormous distances and accumulated information about every thin cloud of plasma it passed through, something precise enough to locate exactly where in the sky it came from, so scientists could build up a statistical picture of the entire intergalactic medium. Nature provided that probe. It had been providing it for years, firing signals from across the universe. Scientists just needed enough of them in the right locations. Fast radio bursts. These events are among the most energetic phenomena in the known universe. They last for a fraction of a second. They carry radio waves that travel billions of light years without losing their basic structure. And crucially, they carry a fingerprint of everything they pass through. When a fast radio burst travels through plasma, the radio waves at different frequencies arrive at slightly different times. Lower frequencies are slowed more than higher frequencies. The total spread in arrival times tells you how much plasma the signal passed through. Measure that spread precisely, and you measure the total electron density along that exact path through the universe. Each fast radio burst is one measurement of one line of sight. One fast radio burst tells you something. 60 precisely located fast radio bursts tell you where the missing matter is. And in June 2025, 60 was exactly what a team had. In June 2025, a research team at the California Institute of Technology published findings that closed a 20-year chapter of scientific mystery. The team had spent years collecting and precisely locating fast radio bursts using a radio telescope array called CHIME, the Canadian Hydrogen Intensity Mapping Experiment, a massive radio observatory built in British Columbia. CHIME scans large patches of sky simultaneously and can detect fast radio bursts across a wide range of sky positions. Locating a fast radio burst precisely is harder than simply detecting one. These signals are brief, lasting milliseconds, and they arrive from across billions of light years. Getting a precise sky position requires comparing the signal's arrival time across multiple telescope dishes and applying detailed calculations. Early fast radio burst detections had rough positions. Recent improvements in technique tightened those positions dramatically. The team collected 60 fast radio bursts that met their precision requirements. For each one, they measured the dispersion, the spread in arrival times between different radio frequencies. Caused by plasma, the signal passed through between its source galaxy and Earth. Each burst came from a different direction in the sky, passing through a different path of intergalactic space. By combining 60 paths with 60 dispersion measurements and the known distances to the source galaxies, the team built a statistical map. They compared the total amount of plasma their signals detected against the predictions from cosmological models of where baryons should be distributed. The result confirmed it. 3/4 of the missing baryons are distributed through the diffuse intergalactic medium, spread across the filaments of the cosmic web. as a hot, thin plasma. The missing baryons were always there. Physics said they should be. 20 years of targeted searches found hints. 60 precisely located radio signals from across the universe finally proved it. The discovery did not change the practical reality of intergalactic space. It is still almost unimaginably empty. 1 atom per cubic meter remains the average density. But the matter that does exist out there, the thin plasma in those 1 atom per refrigerator stretches of void, accounts for roughly half the ordinary matter in the universe. Spread across the filaments between galaxy clusters, it is the single largest reservoir of ordinary matter in existence. More mass exists in that near-invisible plasma than in all the stars of all the galaxies combined. That fact reshapes the picture of what the universe actually is. The stars and galaxies that fill astronomy textbooks, the images of spiral arms and nebulae and bright cores, represent only a fraction of the universe's ordinary matter. The rest floats invisibly in the dark, too hot and too thin to see with most telescopes, threaded through the cosmic web in a state that took decades and 60 radio signals to finally confirm. And those radio signals came from another class of extreme object entirely, one of the most violent recurring events in the known universe. Understanding what creates them and why they carry such precise information is what makes the 60 burst discovery possible. Because a fast radio burst does not form from nothing, something catastrophic makes each one, and the source of that catastrophe is still not completely understood. In 2007, an astronomer named Duncan Lorimer was reviewing archived radio telescope data from the Parkes Observatory in Australia. He found a signal in old recordings that nobody had noticed at the time. It lasted a fraction of a second. It carried more energy in that millisecond than our star releases in 3 days, and it came from billions of light years away. Lorimer and his team published the detection. The scientific community was skeptical. One signal in old data could mean almost anything, including instrument error. The signal sat in the literature as a curiosity. Then more appeared. Astronomers pointed radio telescopes at different patches of sky and waited. The bursts kept coming, brief, powerful, arriving from deep in the universe with no warning. By the mid-2010s, the field of fast radio burst research had become one of the most active in all of astrophysics. A fast radio burst is a pulse of radio waves. It forms somewhere billions of light years away and travels across the universe in a tight beam. The entire pulse fits inside a millisecond, sometimes less. The source is almost certainly a neutron star, specifically a type of neutron star called a magnetar, a stellar remnant with a magnetic field trillions of times stronger than Earth's. When a magnetar releases energy, it can produce a flash of radio waves intense enough to cross billions of light years. The critical feature of fast radio bursts for finding missing baryons is dispersion. Radio waves at different frequencies travel through plasma at slightly different speeds. Lower frequency waves slow more than higher ones. By the time a fast radio burst reaches Earth, its frequencies have been pulled apart in time, with higher frequencies arriving fractions of a second before lower ones. The amount of this spreading, called the dispersion measure, tells you how much plasma the signal passed through. More plasma means more spreading. Precisely measuring the dispersion measure of a fast radio burst gives you the total electron density along its entire path from source to Earth. One burst measures one path through intergalactic space. That is a single data point. Useful, but not enough to map the distribution of matter across the whole universe. 10 bursts give 10 paths. Still limited, the source galaxies might cluster in certain directions, biasing the results. The paths might miss large sections of the cosmic web. 60 bursts spread across different parts of the sky, with known source distances, give a statistical sample large enough to model the overall distribution of intergalactic plasma. 60 is the threshold where the math becomes reliable enough to make a confident claim. The California Institute of Technology team waited for 60. They checked each one for precise position. They verified source distances using optical telescope follow-up observations. Then they ran the statistics. The result held the plasma in intergalactic filaments accounts for the missing baryons, not just some of them, 3/4 of the entire missing population. 60 millisecond pulses from billions of light years away, and a conclusion that quietly rewrote the baryon census of the observable universe. But even knowing where the matter is, the universe keeps one final barrier firmly in place. Most of those galaxies, most of that plasma, most of the cosmic web itself sits beyond a point from which nothing will ever return to us. A boundary built not by physics in the usual sense, but by the expansion of space itself. And beyond that boundary, 94% of the observable universe is sealed off forever. The matter sitting between galaxies is not cold and quiet, it burns. The warm, hot intergalactic medium exists at temperatures ranging from 100,000 to 10 million degrees. At those temperatures, atoms do not hold together normally. Electrons are stripped away from their nuclei by the intense heat. What remains is plasma, a loose soup of charged particles moving at extreme speeds through the near emptiness of intergalactic space. Plasma at these temperatures radiates primarily in X-rays and in a specific band of ultraviolet light called the far ultraviolet. Both of these wavelengths are absorbed by Earth's atmosphere before they can reach ground-based telescopes. Detecting them requires space-based instruments. The Hubble Space Telescope's ultraviolet spectrograph has caught faint absorption signals consistent with this plasma along certain lines of sight to distant quasars. X-ray telescopes like the Chandra Observatory have detected hints of its presence in filaments between galaxy clusters, but the signals are extremely faint. This is why the plasma evaded direct confirmation for so long. Ground telescopes cannot see in the relevant wavelengths. Space telescopes that can see those wavelengths struggle with the signal's extreme faintness. The plasma is simultaneously very hot and extremely thin. High temperature makes it energetic enough to emit certain detectable radiation. Low density makes that radiation so sparse it barely rises above background noise. At 1 atom per cubic meter, even across a span of millions of light years, the total column of plasma along any given line of sight is thin enough to absorb or emit only a faint signal. Each individual measurement risks falling inside the margin of measurement error. The fast radio burst method sidesteps this problem. Radio waves interact with free electrons in a way that does not require the plasma to glow or absorb light at specific wavelengths. The dispersion effect happens simply because electrons are present. So fast radio bursts measure the plasma through its gravitational and electromagnetic effect on passing radio waves, rather than trying to detect its own faint radiation. This is why fast radio bursts cracked the problem when other methods stalled. Different tool, different physical interaction. Same plasma. The plasma threads through the filaments of the cosmic web connecting galaxy clusters. It is not uniformly spread. It concentrates along filaments and thins out inside voids. The densest patches sit in the filaments between massive galaxy clusters, where the cosmic web's threads are thickest. What this means for our understanding of the universe is significant. The stars, galaxies, and gas clouds that fill astronomy images represent a minority of ordinary matter. The majority floats invisibly between those structures in a state so energetic it barely radiates in detectable ways, stretching across the cosmic web in a form that took decades and a completely new observational technique to confirm. Ordinary matter itself, all of it combined, makes up only about 5% of the universe's total energy content. The rest is dark matter and dark energy, even harder to detect and even less understood. So the matter we found, the missing baryons hiding in intergalactic plasma, represents the missing fraction of just 5% of everything. And even with that found, the universe keeps growing, expanding, pushing structures apart faster every year, pushing most of the observable universe permanently beyond our reach. There is a line in space that humanity will never cross. It does not look like anything. It carries no flag. It has no physical surface. But it is as real as any wall, and it marks the edge of everything we could ever theoretically reach, even with infinite time and the best possible technology. Scientists call it the cosmic event horizon. To understand it, you need to understand that space itself is expanding. After the Big Bang, the universe began growing. Every point in space moves away from every other point, the way dots drawn on a balloon move apart as you inflate it. Galaxies are not flying through space outward like shrapnel from an explosion. Space between them is stretching, and it carries the galaxies along with it. This expansion is accelerating. Something scientists call dark energy is causing space to stretch faster over time. Here is the consequence. Light always travels at 186,000 miles per second through space. But if the space between us and a distant galaxy is expanding faster than light can cross it, the light from that galaxy will never reach us. The galaxy moves away from us faster than any signal from it can approach. The distance at which this happens right now is called the Hubble radius, roughly 14 billion light-years away. Galaxies beyond that distance are receding from us faster than light speed. But the cosmic event horizon is different from the Hubble radius. It is the distance from which light emitted today will eventually reach us in the infinite future, given the current rate of dark energy-driven expansion. Anything beyond the cosmic event horizon, about 16 billion light-years away, will never reach us no matter how long we wait. Light from those galaxies is already losing the race against expansion. The observable universe extends about 46 billion light-years in every direction. We can see light from regions 46 billion light-years away because that light was emitted billions of years ago when those regions were much closer, and the universe's expansion has since stretched the space between us. But we can see that old light. We observe those galaxies. What we cannot do is ever interact with the vast majority of them. Of the roughly 2 trillion observable galaxies in the universe, approximately 94% already sit beyond the cosmic event horizon. Any signal we sent toward them today, even at light speed, would never arrive. The expanding space in between grows faster than our signal travels. 94% of what we can see is already permanently sealed off from any possible contact, travel, or interaction. We observe them the way you might look at a photograph of someone who is gone. Visible, unreachable. This number gets more extreme over time. As dark energy keeps accelerating the expansion, more galaxies will cross the event horizon. The observable universe that future civilizations can interact with will shrink even as the universe itself grows. The only galaxies humanity could theoretically ever reach across all of infinite future time are those in our local group, the 50 or so galaxies gravitationally bound to the Milky Way. Gravity keeps them together despite the expansion. Everything beyond the local group is already on a one-way trip away from us. And even within the local group, travel to any galaxy remains impossible with current or foreseeable technology. It is an enormous space where most of the lights are already beyond our reach, and every year that passes adds more galaxies to the list of the permanently unreachable. But the one galaxy that is definitely coming toward us, the one that gravity has already committed to a collision course, is getting measurably closer. Most people learn a rule in school. Nothing moves faster than light. That rule applies to objects moving through space. It does not apply to space itself expanding. Space is not a thing that sits still while objects move through it. Space is a fabric, and that fabric stretches. When it stretches, everything embedded in it moves apart. The speed at which 2 points in space move apart due to expansion is not limited by the speed of light, because space itself is not a physical object moving through anything. It is the background itself, stretching. The current rate of expansion, called the Hubble constant, means that for every 3.25 million light-years of distance between 2 points, those points are moving apart at about 44 miles per second due to expansion alone. That rate sounds modest, 44 miles per second for every 3.25 million light-years of distance. But distance is enormous in this universe. At a distance of 14 billion light-years, That expansion rate adds up to the speed of light. At distances beyond that, the recession speed exceeds light speed. Not because anything is breaking physics, because space itself is growing faster than light can cross it. A galaxy 14 billion light-years away is receding from us right now at exactly the speed of light. A galaxy 20 billion light-years away is receding at roughly 1.5 times the speed of light. We can still see it, because the light we observe left it billions of years ago when it was closer, but any light it emits today will never reach us. This is why the observable universe's edge sits at 46 billion light-years, even though the universe is only about 13.8 billion years old. The regions we observe at 46 billion light-years away were much closer when their light departed. Expansion has since stretched that distance. We see ancient light from a region now located far beyond where that light left from. The expansion is not slowing down. Dark energy, the name scientists give to whatever is causing the acceleration, behaves in a way that increases the expansion rate over time. The more the universe expands, the more dark energy there is, and the faster it expands further. A self-reinforcing cycle with no known stopping point. For the Milky Way, this has one major practical consequence alongside the theoretical ones. Everything outside our local group is on a permanent one-way journey away from us. The Virgo cluster, 50 million light-years away, will eventually recede beyond our event horizon. The great walls and filaments of the cosmic web, hundreds of millions of light-years away, are already far beyond any possible reach. Future astronomers, if they exist billions of years from now, will see a smaller observable universe. The galaxies now on the edge of visibility will have crossed the horizon and gone dark. A civilization 1 trillion years from now would look out and see only the merged remnant of the Milky Way and Andromeda, plus a handful of other local group members. The rest of the universe, all 2 trillion galaxies, would be invisible, unreachable, gone from the sky entirely. We live in a period of cosmic history where the universe is still fully visible to us. That window is closing, galaxy by galaxy, year by year, and while it closes, the one galaxy guaranteed to reach us is getting closer every day. The approach is invisible at human timescales, but the physics is locked in. The collision is already underway in slow motion. 2 trillion galaxies sit inside the observable universe. 2 trillion separate islands of stars, gas, dust, and dark matter, each containing hundreds of billions to trillions of stars, each separated from us by distances that range from tens of thousands of light-years to 46 billion light-years. Of those 2 trillion, humans have meaningfully studied a tiny fraction. The Milky Way and its immediate satellites receive the most detailed attention simply because they are here. Nearby galaxies like Andromeda and the Magellanic Clouds have been mapped in detail across multiple wavelengths. A few thousand galaxies within the local universe have good distance measurements, stellar population studies, and chemical analyses. Beyond that, most galaxies are known only by position, rough distance, and basic properties inferred from their light. The observable universe is enormous, and humanity has studied a rounding error of it. Exploration, in the physical sense, is effectively impossible. As established, even reaching the nearest dwarf galaxy would take Voyager 749 million years. Crossing to Andromeda at light speed would take 2.5 million years. Any physically realistic spacecraft falls far short of light speed, making those timescales even longer. The vast majority of the 2 trillion galaxies are not just practically unreachable, they are permanently beyond the cosmic event horizon. What exploration actually means for humanity, in the context of the universe, is exploration through light. We send and receive photons. We build instruments to detect different types of radiation. We gather information across the electromagnetic spectrum, from radio waves to gamma rays, and we use that information to reconstruct the properties of objects we will never physically visit. The James Webb Space Telescope observes galaxies from the universe's early history galaxies that formed less than 1 billion years after the Big Bang. It collects the oldest light in existence and extracts from it the chemistry of ancient star-forming regions. No probe will ever visit those galaxies. No human will ever stand near them. But the information in their light is real and measurable and tells us how the universe grew from its earliest structures. Radio telescopes map hydrogen gas across billions of light years, revealing the structure of the cosmic web through patterns in how gas absorbs and emits radio waves. X-ray observatories detect galaxy clusters by their hot gas, locating the densest nodes of the web. Gravitational wave detectors pick up ripples from black hole mergers billions of light years away, opening a completely new channel of information about the universe that requires no light at all. Humanity explores by listening, by collecting, by measuring. The universe speaks in radiation, and we have built increasingly sensitive ears to hear it. The 2 trillion galaxies we can see and never touch are not a wall of loss. They are an archive. Each one carries information about a different part of the universe's history, a different environment, a different stage of cosmic evolution. The science of observing them has already revealed the structure of the cosmos, the age of the universe, the existence of dark matter and dark energy, the history of star formation across billions of years. But the universe still holds one future event that will physically, directly, inevitably affect the galaxy we live in. Andromeda is falling, and the numbers describing its approach and what the collision will and will not destroy are some of the most counterintuitive facts in all of astrophysics. 2.5 million light-years of space sit between the Milky Way and Andromeda right now. That distance is shrinking. Astronomers have measured the motion of Andromeda relative to the Milky Way using multiple independent methods. The most precise measurements come from the Hubble Space Telescope, which tracked the positions of stars inside Andromeda over several years with extreme accuracy. Those measurements revealed that Andromeda is moving toward us at roughly 68 miles per second. 68 miles per second sounds fast. Compared to the distance it needs to cover, it is extremely slow. At that speed, closing 2.5 million light-years takes approximately 4.5 billion years. The approach is invisible at human timescales. Watching Andromeda in the night sky year after year, century after century, reveals no visible motion. The galaxy is too far and the timescale too vast for any human lifetime to perceive. The movement only becomes visible through precise mathematical analysis of tiny positional shifts measured over years. But the physics locks it in. Gravity between the Milky Way and Andromeda, combined with their initial velocities, produces a trajectory that ends in collision. They have been falling toward each other for billions of years already. The Hubble measurements also revealed something important about the direction of Andromeda's motion. It is approaching mostly head-on, meaning the bulk of its velocity is directed toward us rather than sideways past us. Earlier models suggested Andromeda might pass by at a glancing angle, perhaps swinging close without a direct collision. The Hubble data tightened that picture. The approach is primarily radial, meaning a direct collision is the most likely outcome. Some uncertainty remains in the exact trajectory. Andromeda also has a slight sideways component of motion, and the total mass of both galaxies, including their dark matter halos, affects the precise path. Dark matter halos extend far beyond the visible edges of each galaxy, and accurately measuring the total mass of both dark matter halos is still an active area of research. Different mass estimates shift the timing and geometry of the collision by hundreds of millions of years in either direction. What is not uncertain is the outcome. A collision is coming. Both galaxies are gravitationally committed to this encounter. No force known to physics will stop it or divert it. The collision will not happen suddenly. Galaxies do not crash the way cars crash. The first close pass will take tens of millions of years to complete. After the first pass, gravity will pull the two galaxies back together for a second pass, then a third. Each pass will mix the stars, gas, and dark matter of both galaxies further. The full merger, where both galaxies settle into a single combined structure, will take roughly 1 billion years after the first contact. What that settled structure looks like, and where Earth sits within it, is one of the most vivid futures science has ever simulated. And it looks almost nothing like what most people imagine a galactic collision to be. When people hear two galaxies colliding, most picture something like a cosmic car crash. Stars smashing into each other, explosions, destruction across the board. The reality is far stranger and in some ways more unsettling because of how empty galaxies actually are. A galaxy is mostly empty space. The stars inside a galaxy are separated by enormous distances relative to their own sizes. Our nearest stellar neighbor sits about 4 light-years away. 4 light-years is roughly 24 trillion miles. The star itself is about 860,000 miles across. The distance between stars is millions of times larger than the stars themselves. Imagine a basketball representing our star. The nearest neighboring basketball, at the same scale, would sit roughly 4,500 miles away, one basketball in the eastern United States, and the nearest neighbor on the other side of the continent and into the Pacific Ocean. Now smash 2 collections of basketballs together. Each collection millions of basketballs scattered across millions of miles. How many basketballs actually collide? Almost none. The individual objects are so small relative to the gaps between them that 2 whole galaxies can pass through each other, and barely any stars will physically collide. What happens instead is a gravitational drama. As the Milky Way and Andromeda approach, their gravity pulls at each other's structure from across hundreds of thousands of light years. Long streamers of stars will be pulled out of both galaxies, flung into wide arcs around the collision site. Stars will be ejected from their normal orbits and sent onto completely different trajectories. Some will be flung into deep intergalactic space, freed from both galaxies entirely. The gas clouds inside both galaxies will not pass through each other as cleanly as stars do. Gas clouds can collide, compress, and trigger massive waves of new star formation. Simulations of the Milky Way and Andromeda merger predict enormous starbursts, periods where new stars form at rates far higher than the current quiet pace of star formation in either galaxy. The collision will light up the combined galaxy with new stars, some of them massive enough to explode as supernovas within just a few million years of forming. The central regions of both galaxies contain supermassive black holes. The Milky Way's central black hole, called Sagittarius, a star, contains the mass of about 4 million stars like ours. Andromeda's central black hole is estimated to contain the mass of roughly 100 million similar stars. When the galaxy cores merge, these 2 black holes will begin orbiting each other. Over hundreds of millions of years, they will spiral inward and eventually merge in a collision that will release gravitational waves, ripples in space-time, of extraordinary power. For planets orbiting stars far from the galactic cores, the collision's direct physical effects may be surprisingly subtle. The gravitational tidal forces reshape orbits of stars and planetary systems over millions of years, but slowly enough that individual planets are unlikely to be immediately disrupted in most cases. The visual spectacle from any surviving planet will be extraordinary. 2 galaxies filling the sky, new stars igniting across previously dark regions, a sky transformed beyond anything a human eye has ever seen. 4.5 billion years from now, the Milky Way and Andromeda will make their first close pass. 4.5 billion years is approximately the current age of our solar system. The Earth formed about 4.5 billion years ago from a disk of gas and dust around a young star. Everything Earth has gone through, every geological era, every mass extinction, every ice age, the entire history of life from single cells to every species alive today, unfolded across roughly 4.5 billion years. The same length of time stretches ahead before the collision begins. That timeline sits alongside another major event in our solar system's future. In roughly 5 billion years, our star will begin its exit from the main sequence phase of its life. As its hydrogen fuel runs low, it will expand outward into a red giant, growing large enough to potentially reach or exceed Earth's current orbital distance. So the collision of the galaxies and the end of our star's stable phase will happen within roughly the same cosmic timeframe, give or take hundreds of millions of years. Whether Earth still exists in any recognizable form by then is a separate question, but the two events bracket the same era of the future. The collision itself unfolds in phases. The first close pass takes perhaps 300 million years to complete, from initial contact to when the two galactic cores swing past each other. After the first pass, gravity pulls them back. The second approach will happen several hundred million years after the first, then a third pass. Each successive pass takes less time as energy dissipates. Roughly 2 billion years after the first contact, the two galactic cores will begin to merge. The separate identities of the Milky Way and Andromeda will dissolve. Stars from both galaxies will mix into a single structure. The combined galaxy, which some scientists have nicknamed Milkomeda, will settle into a shape determined by the combined mass, angular momentum, and energy of both systems. Simulation models suggest the merged galaxy will likely be elliptical in shape, meaning it will lack the ordered spiral arms that currently define both the Milky Way and Andromeda. Spiral structure requires an ordered rotation pattern that violent mergers tend to scramble. The combined galaxy will probably look more like a smooth, rounded blob of stars than either of its parents. The total time from first contact to settled merger roughly 1 billion years after the initial pass. So approximately 5.5 billion years from today, a single merged galaxy will exist where two separate spirals once stood. For Earth, if it still exists at any stage of this process, the night sky will change profoundly. In the billions of years before the first pass, Andromeda will grow visibly larger in the sky as it approaches. By the time of first contact, it will fill enormous stretches of the sky. During the merger phases, two galactic cores will glow in the sky simultaneously, and streams of displaced stars will arc across the heavens in patterns no current star map anticipates. But whether Earth survives to see any of that depends on forces even closer to home. And what those forces will do to the inner solar system is one of the most genuinely uncertain parts of this entire future story. Milkomeda will be an elliptical galaxy. That single sentence represents one of the most dramatic transformations in the future history of this part of the universe. Right now, both the Milky Way and Andromeda are spiral galaxies. Flat disks with sweeping arms, rotating in an ordered pattern, filled with lanes of gas and dust where new stars form. Spirals are dynamic, active, star-forming systems. Ellipticals are different. An elliptical galaxy is a smooth, rounded or egg-shaped collection of stars, usually older, usually with less active star formation than a spiral. The ordered rotation that creates spiral arms gets disrupted during a major merger. Stars end up on a wide variety of orbital angles instead of all moving in the same rough direction. The result is a puffy ball of stars on crossed orbits rather than a flat spinning disk. Milkomeda will contain roughly 1.5 trillion stars combined, adding the Milky Way stars to Andromeda's. The merged dark matter halos of both galaxies will create an enormous gravitational structure surrounding the whole system. The central region will be dominated by the merged supermassive black hole, formed when both galactic centers sink toward each other and eventually combine. As for Earth, and where our solar system might end up inside Milkomeda, the answer is genuinely unknown. During the merger, gravitational interactions will radically alter the orbits of most stars. Stars currently in the Milky Way's disk may end up on completely different orbits in the merged galaxy. Simulations run by astronomers suggest our solar system could be flung outward toward the outer halo of Milkomeda, or could remain somewhere in the interior, or could theoretically be ejected into intergalactic space during one of the close passes. The probability of ejection into deep intergalactic space is relatively low in most simulations, roughly a few percent. More likely, the solar system stays gravitationally bound to the merged system in some orbit. But wherever the solar system ends up within Milkomeda, the night sky will be transformed. Currently, the Milky Way appears as a band of light across the sky because we sit inside its flat disk and see the galaxy edge on in all directions. In the merged elliptical Milkomeda, that structure would be gone. Stars would surround the solar system from all directions in a more spherical distribution. The band of the Milky Way as we know it would disappear, replaced by a glow that comes from every direction. And eventually the starbursts triggered by the merger will fade. The gas clouds that fueled new star formation during the collision will be consumed or dispersed. Milkomeda will settle into a quieter state, an old galaxy mostly burning through its existing stars without making many new ones. The galaxy we live in will still exist, just unrecognizable, and the dark matter that binds it all together, the invisible glue holding galaxies and galaxy clusters in place, plays a larger role in the collision's exact path than most people realize. Understanding how dark matter shapes the merger also reveals how little we still know about the most abundant substance in the universe. Every galaxy sits inside an invisible sphere of mass. Dark matter halos surround galaxies and galaxy clusters, providing most of the gravitational force that holds them together and shapes their behavior over billions of years. The Milky Way's dark matter halo extends hundreds of thousands of light-years beyond the galaxy's visible edge. Andromeda's halo is comparable in size. Dark matter does not emit light. It does not interact with electromagnetic radiation in any known way. We cannot see it, photograph it, or directly detect it with any current instrument. Its existence is confirmed through its gravitational effects. The rotation curves of galaxies, the bending of light around galaxy clusters, and the large-scale structure of the cosmic web all require enormous amounts of unseen mass to explain the observations. For the Milky Way and Andromeda collision, dark matter matters enormously. The total mass of both galaxies, which determines the strength of gravity between them and therefore the timing and path of the collision, depends mostly on the mass of their dark matter halos rather than on the stars and gas we can see. Visible matter accounts for only a small fraction of the total mass. Measuring dark matter halo mass is difficult. Scientists use several indirect methods: the velocities of satellite galaxies orbiting the main galaxy, the dynamics of stellar streams left by disrupted dwarf galaxies, and gravitational lensing effects on background light. Each method gives an estimate, and those estimates carry significant uncertainty. Current estimates for the Milky Way's total mass, including dark matter, range from about 500 billion to over 1.5 trillion times the mass of our star. That is a factor of 3 in uncertainty across different measurement approaches. Andromeda's mass estimates carry similar ranges. This mass uncertainty propagates directly into the collision timeline. If both galaxies are at the higher end of mass estimates, their mutual gravity is stronger, and the collision happens sooner. If they are at the lower end, gravity is weaker and the timeline shifts later by hundreds of millions of years. The 4.5 billion year estimate is the central value from the best current models, but the true range of reasonable estimates spans from about 3.5 billion to over 5 billion years, depending on the mass assumptions. Additionally, the Milky Way and Andromeda are not approaching each other in isolation. The gravitational influence of other members of the local group, particularly the Magellanic Clouds and the Triangulum Galaxy, adds small perturbations to the trajectory. The large Magellanic Cloud in particular, with its substantial mass, creates measurable distortions in the Milky Way's dark matter halo that could slightly alter the collision geometry. Dark matter is the biggest unknown in all of this. Scientists are confident the collision will happen. The gravity is real, the approach velocity is measured, and the trajectory is mostly radial. But the precision of the prediction depends on a substance we cannot directly observe, whose total mass we can only estimate within a factor of 3. and whose detailed distribution within both galaxies is still being mapped. A mystery at the heart of the biggest future event in our galaxy's history. And as uncertain as the timing is, one thing the merger will definitely bring closer is not another galaxy. It is the aging of our own star, and what that aging means for Earth deserves to be said directly. The galactic merger itself presents almost no direct physical danger to Earth. As established in an earlier chapter, the gaps between stars in a galaxy are millions of times larger than the stars themselves. During the entire merger process, which will unfold over roughly 1 to 2 billion years of active mixing, the probability of our solar system experiencing a direct stellar collision is extremely small. Simulations consistently find that fewer than a handful of individual solar systems across both entire galaxies will experience close enough stellar approaches to seriously disrupt their planetary orbits. The bigger gravitational shifts will be gradual. Over millions of years, the solar system's orbit within the galaxy will change as the Milky Way's overall structure gets pulled apart and rebuilt. These changes are slow by human standards, even slow by geological standards, and they do not necessarily translate into immediate danger for individual planets. The real danger for Earth on these timescales comes from our own star's life cycle, not from any neighboring galaxy. Our star will spend roughly another 5 billion years in its current stable phase, burning hydrogen in its core and maintaining relatively constant energy output. During that time, Earth's surface will gradually warm, not dramatically year to year, but measurably over hundreds of millions of years, because the star slowly brightens as its core composition changes. Current models suggest Earth's surface becomes too hot for liquid water in roughly 1 billion years, before the star even begins its red giant expansion. After roughly 5 billion years, the star exits its stable phase. It begins expanding, growing into a red giant that will swell to many times its current size. The inner planets face increasing radiation and potential engulfment. Earth's fate during this phase is uncertain. Some models show it getting swallowed, others show it pushed slightly outward by mass loss from the expanding star and surviving outside the expanding surface. So the timeline looks like this: 1 billion years until Earth's oceans may become unsustainable, 5 billion years until the star's red giant expansion begins, 4.5 billion years until the galactic merger's first contact. All of these events cluster in the same cosmic era, within a few billion years of each other. Earth's window of habitability will likely close long before the galactic merger becomes dramatic. Whatever watches the two galaxy cores merge overhead, whatever experiences the transformed sky of Milkomeda, will almost certainly not be anything that evolved on today's Earth. The danger from Andromeda approaching is not a direct physical strike on our planet. It is simply that the universe is enormous, old, and indifferent to the existence of any particular planet. The merger is one event in a chain of changes that will transform this solar system over timescales far longer than the entire history of life on Earth. Looked at from that scale, our entire civilization occupies a thin slice of time between a young, stable star and an eventual transformation the planet will never survive. And yet from inside that slice, we have managed to map the entire situation. Every galaxy, every distance, every future event. We have measured the approach of Andromeda. We have found the missing matter between galaxies. We have located our position inside a cosmic web spanning billions of light years. One galaxy among more than 2 trillion. One planet around one star. And somehow, this is where the measuring happened. For most of human history, the Milky Way was the universe. Then Andromeda proved it was a neighbor. Then the full count of neighbors began. Today, astronomers have confirmed over 80 galaxies in the local group, the gravitationally bound collection of galaxies surrounding the Milky Way and Andromeda. Most of them are dwarfs, tiny, faint, irregular collections of stars that would be invisible from even a modest distance. The Milky Way and Andromeda dominate the local group by mass and star count. The other members cluster around them as satellites, pulled into orbit by the gravity of the two large spirals. Some of these dwarf galaxies were only discovered in the last few decades. Many were found using new sky surveys that map faint objects across large areas of sky. Some, like the dwarf galaxies found in the Virgo constellation region of the sky, were discovered by analyzing density variations in star counts, the same method that uncovered the Canis Major and Sagittarius dwarfs. The local group spans roughly 10 million light-years from its outermost confirmed members to its opposite edge. To cross the entire local group at light speed would take 10 million years, 4 times the age of Andromeda's light currently reaching us. Beyond the local group sits the next major collection, the Virgo cluster, about 50 million light-years away, containing over 1,300 confirmed galaxies. Not a cluster of individuals, but a gravitational knot of thousands. The Virgo cluster forms the center of a larger supercluster called the Virgo supercluster, which contains the local group as one of its smaller members. And then Laniakea, the supercluster of superclusters to which the Virgo supercluster belongs, spanning roughly 500 million light-years. Our local group is one node in that structure, which itself is one node in the observable universe's web. Standing at Earth and mapping outward, each scale reveals a new layer of structure: our solar system, our galaxy, our local group, our supercluster, the observable universe. Each layer is larger than the previous by a factor that removes the human scale entirely. The distance to Andromeda, 2.5 million light-years, marks the first step outside our own galaxy. And even that first step is so vast that Voyager, our fastest machine, would spend 749 million years crossing just to reach the nearest dwarf galaxy, a fraction of that first step. Every fact in this story exists inside the local group, or between us and the edge of the observable universe. Both the objects closest to us and the structures billions of light-years away follow the same physics, shaped by the same forces, expanding inside the same universe. And that universe, taken all at once, has a scale problem that human minds cannot solve. The final picture, stacking all these distances together in one image, produces something that breaks every comparison we have used in this entire story. Every number, every metaphor, every careful comparison to familiar objects adds up to one final confrontation with the real scale of what exists. Start small. Our solar system, the distance from Earth to our star, is about 93 million miles. A beam of light covers that in about 8 minutes. The outer edge of the solar system, where Voyager now drifts, sits about 14 billion miles away. Light takes roughly 20 hours to cross it. Step out. The nearest star system, Alpha Centauri, sits about 4 years away. Light takes 4 years. Voyager would take 75,000 years. That is one step to one neighbor star. Step out further. The Milky Way stretches 100,000 light-years from edge to edge, 100,000 years of light travel just to cross our home. Voyager would take about 1.5 billion years. Now step to our nearest galactic neighbor, Canis Major, at 25,000 light-years, tucked into the outer disk, closer than our own galaxy's core. Then the Sagittarius dwarf at 70,000 light-years, being eaten alive. Then the Large Magellanic Cloud at 179,000 light-years. Then the Small Magellanic Cloud at 210,000 light-years. Then Andromeda, 2.5 million light-years. The first step outside our galaxy's immediate surroundings, light leaving Andromeda tonight, began its journey before humans existed. Voyager would need a time greater than the current age of the Earth, multiplied many times over, to cover that distance. The local group spans 10 million light-years, 80 galaxies, most of them dwarfs, all of it falling inward, eventually destined to merge into a single structure over tens of billions of years. The Virgo cluster at 50 million light-years, over 1,300 galaxies in a gravitational knot, the nearest major cluster outside our local group. Light from it left during a period when the most complex life on Earth was early mammals, the Virgo supercluster at several hundred million light-years, Laniakea at 500 million light-years. Our local group is one of 100 or more galaxy groups inside Laniakea, and Laniakea is one structure among thousands of similar superclusters across the observable universe. The observable universe, 46 billion light-years in every direction, containing roughly 2 trillion galaxies, 94% of them already beyond the cosmic event horizon, permanently unreachable. The matter between those galaxies, counted and confirmed in June 2025 using 60 fast radio bursts, forms the warm-hot plasma of the intergalactic medium, holding more ordinary matter than all the stars in all those galaxies combined. And all of that, every galaxy, every filament, every void, every plasma atom floating alone in a refrigerator of space, every light year, every collision and merger and future transformation, is the observable universe. The universe may extend far beyond what we can observe. Cosmologists believe the universe is much larger than the observable portion. Some models suggest it is infinite. If so, everything described in this story, every galaxy and cluster and supercluster, everything humans have ever measured or mapped or detected, would be a rounding error inside something without edges. One planet, one star, one solar system inside one galaxy, among 2 trillion. And yet, this is where the measuring happened. Every distance in this story was calculated from here. Every galaxy was found from here. Every confirmation, every theory, every mystery still unsolved was built from instruments on this one small world. The universe is incomprehensibly large, and you are standing inside it. That is where we end. If this journey was worth your time, a like and subscribe helps us keep going. And if you stayed until the end, you already know the universe does not give up its secrets easily. Neither should you.